So today we're going to take a look at wholes and how this limit notation works with wholes. So if you look right here, our whole is at x equals 3. So our limit notation, as it approaches the whole from the left-hand side, what value does our y approach? Well, it approaches a height of 1. And it's the same thing if it's coming from the right-hand side. It's approaching a height of 1. So as x approaches from the left, the f of x approaches 1. And it's the same thing for here. It approaches 1. So you'll notice this is different than our vertical asymptote. So for example, our vertical asymptote right here, if we were to say the limit of f of x as x goes to negative 3 from the left-hand side, on the left-hand side it's going to negative infinity, and our limit of f of x as x goes to negative 3 from the right-hand side is positive infinity. So you'll see how that whole is different. It's going towards a value. So let's take a look at this one. Okay, so I can factor out a 10. So this would be x plus 3. And what would the bottom factor in do? Well, is x plus 3, x minus 2. So we know that there's a whole right here, or excuse me, a vertical asymptote at positive 2. If we look at our horizontal, the top is less as x gets really, really big. It's a big number over a huge number, right? Because we're kind of just with the 10x over x squared. So that's just 10 over x. So it is at, our horizontal is at 0. And let's see, our y-intercept, 30, let's see, if we plug in 0 for x, 30 over negative 6 is negative 5. But we know that there's a whole at negative 3. So this simplified to 10 over x minus 2. If I plug in negative 3, I get 10 over negative 3 minus 3. So 10 over negative 6, which is negative 1 2/3. So our notation, that tells us our whole is at negative 3, negative 1 2/3, so right here. So we know that this swoop one looks something like this. So our notation, the limit of g of x as x goes to our whole from the left, and our limit of g of x as x goes to our whole from the right. Now if it's going to our whole, it's going right to that same height here. All right, so hold on one second here. So we could say our whole is at negative 1 2/3. It's approaching that height. Oh, I messed up. This is x minus 2. Okay, I thought this was weird. I was trying to figure out why this is wrong. So let's look at that again. I was like, I can't believe they gave us a fraction for that one, for our first one. So this is 10 over x minus 2. And if we put in our whole, it's 10 over negative 3 minus 2. 10 over negative 5 or negative 2. So our whole should actually be down here. So it approaches negative 2. So to figure out where it approaches, we just take our whole and we can plug it into the equation. Now numerically, again, you can take this and you can just start plugging in these values. So negative 3.1 is negative 1.96. 3.01, negative 1.99, 0.1, negative 1.9996, and add another 0, and negative 1.9996. So we can see as we're getting closer to 3, because again, if here is negative 3 on our number line, we started at negative 3.1, And we're moving the values closer, and we can see that it's getting closer to -2. It's the same thing if we go the other way. -2.9, -2.04. Add another 9, -2.004, -2.0004, -2.00004. So you can see how either direction, right, if this is -2.9, as we move closer, our values are getting to -2. Now, when we take a look at this next one, what do we notice here? Well, I notice that there's a hole right here. And so all this simplifies to is there's a hole at x equals 1, right? And, well, so our equation, our simplified form, is -x squared plus 2x plus 4. Well, I'm going to see if I can factor this. So let's see, it multiplies to -4 and adds to 2. Well, I can't quite factor that. And so I won't have you graph it if you can't factor it and figure out the zeros. So if we were to go to Desmos here, and let's see, so we had -x squared plus 2x plus 4 times x plus 1 over x plus 1. Hopefully that's what we had. So you'll notice it looks like a parabola here, right? So we can make a rough sketch of it. So we have our parabola. So it looks like a polynomial, right? It looks like that polynomial, but there's a hole at 1. So if I plug in 1, -1 squared plus 2 times 1 plus 4, let's see, that is 1 plus 4 is 5. So at 1, 5, there actually is a little hole right there. So even though it doesn't look like our traditional swoopy rational function, it can still look like a polynomial. So holes, let f of x be a function with our numerator and denominator, polynomials. The holes of a rational function occur at all factors whose multiplicity in the numerator is greater than or equal to the multiplicity in the denominator. So what this is saying is if we have this, and if we were to factor the bottom, right, we know that our domain, it's missing 2 and -6. So we could say all reals, x can't be -6, x can't be 2. Otherwise, we could say -∞ to -6, -6 to 2, and then 2 to infinity. Our vertical asymptotes are at -6. We know there's a hole at 2. Horizontal, we can look at the degrees and they're the same, so it's just at y equals 1. Zeros, so that's like saying when does x minus 2 over x plus 6, so it's at x equals 2. And our end behavior, so what happens is x gets really, really big. Well, as x gets really, really big, right, it's a big number over a big number, so it's at just 1. So our limit of h of x as x gets really, really big, it's at 1. And then our limit of h of x as x gets a lot smaller, we'd have a big negative over a big negative, it's also at